All right, now to just wrap up, the optional extension for alternative methods you can use for hypothesis tests or confidence intervals between two means. And so, again, the two other ways you can deal with those kinds of problems that are not quite as common but still possible could be one where the two population standard deviations are both known. In that case, the test statistic will be a z-score instead of a t-score, and you use the standard normal distribution. Then the second case, which could be a bit more likely, is that the two population standard deviations are unknown, but they're assumed to be equal. Then you use what's called a pool of the sample variances. And so they will find that they basically just have slightly different formulas, but a lot of the general principles are the same. So say in the first case where the two population standard deviations are known, then you'll be finding a z-score, and then still just taking the difference of their sample means, subtracting their hypothesized difference for a test statistic, then dividing by, instead of this time with sample variances, their population variances in here, just divided by their respective sample sizes. Then the p-values or critical values can be found using technology. There's not anything available in StatsMedic, or you can use table A-2, which that's the z table. Then again, both methods just use that standard normal distribution. Then if you want to find a confidence interval between the two means where the population standard deviations are known, again, you're just taking those sample differences, adding and subtracting the margin of error. And then this time the margin of error is just found using that z critical value, and then times, and so that's square root of population 1 variance divided by its sample size plus the population 2 variance divided by its sample size. So in the second case, where we don't know what the population standard deviations are for the two groups, but we're assuming that they're equal, which this could be more likely because, say, for example, you're doing an experiment and the two groups have very similar treatments. So that's why this could be a little more common. In this case, the test statistic will still be a t-score, and then so you're still doing the sample means minus their hypothesized difference. Now divided by this time, so this is a pooled sample variance, is what that s squared sub p stands for. Notice it's just being divided by the first sample size plus that divided by the second sample size. Now here, find the pooled sample variance is taking, so the first sample's degrees of freedom multiplied by its variance plus the second sample's degrees of freedom multiplied by its variance. All of that's divided by both degrees of freedom added up. And then when you actually look up the t-score value, you'd use degrees of freedom, both sample sizes added together, then minus 2. And then the confidence interval estimate for this case, where we're assuming the standard deviations are both equal, is just still taking sample mean differences, adding and subtracting a margin of error. And this time to get the margin of error, we just use that same t critical value. So using degrees of freedom, both sample sizes added together, then minus 2. And this time we're just using that same pooled variance divided by first sample size plus pooled variance divided by the second sample size, all in square root. And this is just a little visual, just to kind of emphasize all three of those methods put together. So starting with the most common, so are the population standard deviation known? No. Then can it be assumed that they're equal? No. And so then you approximate this method using the t distribution and with the standard error square root of both their sample variances divided by their sample sizes. So that'd be the most common. Second most common would probably be if we still know the population standard deviations, but they're assumed to be equal. That's where we'd use that pooled sample variance, which is that formula there again. Then the next one, which could happen, but is probably least likely, is if the standard deviations are both known. And in that case, then you'd use just that standard error where you're actually using the population variances divided by their sample sizes.